We just did a quick review of differential equations. And so now let's talk about boundary value problems for differential equations. That's where you're given not only the differential equation itself, but boundary conditions. And if you have a second order equation, you need two conditions to fully get the full answer without using arbitrary parameters. So the general solution to this equation is this. And I'm kind of cheating here. I'm using a method that I wouldn't hold you responsible for, but anyway, here's the general solution. If you needed this thing, I would put it on a formula sheet and not make you solve for the general solution. But once we have the general solution, all that does is solve the equation itself, and it requires two arbitrary constants. To find out what these constants are to meet the whole problem, we just substitute in this general solution into this equation, and we end up getting two equations for the two unknowns, for these two parameters, C1, C2. So we're going to need, because a boundary condition in this case is on a derivative, we need to find the derivative of the solution. So we needed to take that derivative. Then we plug in 0 because that's where that condition is given. And we get this relationship, which at least relates the two parameters. Then for the other condition, we just substitute in 1 for the argument x. And in effect, we're just solving for two equations and two unknowns. We solve for C1 and C2, and here's that solution. I'm not stepping through this in super detail here. It's just to reacquaint you with the concept of boundary value problems or differential equations. Here's another one. Here's the equation, and here are the boundary conditions. If you go back to a previous slide, this equation is on that previous slide. I forget which one it is. I think it's this one, maybe. Where alpha equals 1, I believe. So we get the solution from this guy. So now we plug in the boundary conditions again. We're going to need the derivative, so we have to find the derivative. And then plug in for both these conditions are at 1, at the argument of 1. Again, two equations, two unknowns. We solve for the two parameters. They're both 1 in this case. So here's the complete solution that satisfies both the equation and these boundary conditions. That's the idea of a boundary value problem. There's some other boundary conditions that are going to crop up later in the course. Sometimes it's just that the function has to be bounded everywhere, including at the endpoints of an interval, perhaps. Here's where we recall some of the features of some of those solutions. Like Bessel functions of the first kind, they're bounded for all x, for all arguments. Bessel functions of the second kind are unbounded at the argument of 0. The Legendre polynomials, the polynomials are bounded on the whole interval of convergence, including the two endpoints. The other solution, the one that wasn't a polynomial that got truncated, that's unbounded at two endpoints. So if you require your solution to be bounded even at the endpoints, you won't be able to use this second particular solution. I guess I'll state this. There's Legendre equations where n is not an integer, but they are neither continuous nor bounded on this interval. So we're going to end up, we'll reject those solutions later in the course. How much I can get through this thing. Here's a boundary value problem with a certain parameter in the equation. We want to find out what parameters give you so-called non-trivial solutions. Since in this case, if y equals 0, it satisfies everything here, including the boundary conditions. We don't want those solutions. We call them trivial, and we're not going to want them. So how do we go about doing this? Well, we're going to have three cases of what lambda is: positive, negative, and exactly equal to 0. So if it's negative, we're going to say it's minus some alpha squared. Alpha is going to be a positive number by the way we define it. And if you go back to our cheat sheet of solutions to differential equations, that means that here's the solution for negative lambdas. And I used the hyperbolic trig one because x is only between 0 and L here. That's a finite range. So that's why we use the hyperbolic trig version of that solution. If the alpha or the lambda is exactly equal to 0, we get this linear solution. Again, go back to our cheat sheet. And if lambda is greater than 0, we'll say it equals some alpha squared. Again, alpha is greater than 0. And it has this solution. These solutions all come from way back on our cheat sheet. These guys. In fact, they're these three equations. These solutions, and we're picking this format because the extent of the x variable was finite. So let's go through those three cases. I think I'll save this for another recording because I don't want to go through this too fast.